Hello everyone, I am going to post this first video. This is video number 1 of 4 that you will actually look at in this module. And this is just an introductory video, so it'll be short and I won't go into a lot of detail because I'll save that for the fourth video, which is going to be the one that's a lot longer. First thing we're going to do is we're going to recap kind of what we did last week, and then I'm going to prepare you for what you're going to be dealing with this week. Last week, we looked at a single variable linear regression model. We picked two variables from the Boston housing data set. The first one was RM, which was an indicator of the average number of rooms in a particular neighborhood. And the second one was MEDV, or median value, which was the median value of the homes in that neighborhood. So we tried to show how we could use the RM variable as a predictor for the median variable that was going, or median value variable that would be applicable to each specific neighborhood. So we set up a linear model in R, and the linear model in R was going to allow us to find the slope and the intercept. Then we built a model where our median value was set equal to the intercept plus the average number of rooms times the slope. We were able to predict values for the median value, and we were able to show the error. And the error, of course, was the difference between the predicted value and the actual value for each of our 506 neighborhoods in that data set. When we ran that model, we got an awful lot of error. And we got an awful lot of error because there's quite a lot of difference between the predicted value and the actual value. And that really comes from the fact that there is just, the one variable wasn't a great predictor of the other. There's just not a lot of correlation between those two variables. And when we do linear regression and we're trying to predict what the outcome variable is going to be, it helps best when we have two variables or more variables where there actually is a real relationship that exists between them. Because it's kind of hard to have two variables that are not correlated and try to build a predictive model using one to predict the other. So that gave us a lot of error. So what we're going to do now is we're going to turn our attention to a different way of doing regression. And the way we're going to do that is we're going to use multiple input variables. And that's what we're going to talk about when we talk about multiple linear regression. So a little bit more about multiple regression. Back to kind of recap, when we use regression to predict likely outcomes, we can sometimes use just one variable, but we're likely to have more error. So imagine if we could use more than one variable. We find variables that collectively together can do a better job of predicting what the outcome variable is going to be. And imagine if that made our model much stronger and much more accurate. So as an example from the Boston housing data set, we could say instead of just using the RM variable to predict the median value, what if we use the RM and the tax variables together? RM can account for some of the variability and tax can account for other parts of the variability, and together they can build a much stronger predictive model. So we would get an intercept, which we always get just one intercept in any regression model, whether it be single variable or multiple variable, and then we would get two slopes. One would be for the room variable and the other would be for the tax variable. And then we would set up an equation that said median value is equal to our intercept plus our room variable times its slope plus our tax variable times its slope. And the slopes are really called coefficients, so we'll start probably referring to those more as coefficients rather than slopes, because that's kind of the standard nomenclature in linear regression. So assuming we've selected wisely, we will get a much more accurate model. So this is the first of 4 videos that I want you to watch. There are 2 others, actually 3 others. The next 2 are going to be videos from a guy by the name of Brandon Fultz, who's a statistician, and he posts all kinds of videos, really well-produced videos, on many things having to do with statistics. What I have done is I've selected the first 2 of his videos on multiple regression, and he does a great job explaining multiple regression. So I think it'll be a good way to introduce the topic. He does other videos that follow after the first 2, and you can watch those if you want, but you don't have to, because I think the first 2 will give you everything you need to get a pretty good understanding of multiple regression. Then what we're going to do after you watch kind of the general information about multiple regression, we're going to then pop over to a video that I've created where I've given you a fairly complex script in R. It's an R script. And I want you to look through the video and walk through the video with me because it does a lot of things. It doesn't just do a multiple regression model, but we're taking a data set, we're paring down the data set, we're dividing it into a training set and a validation set. Then we're running correlations, plots, multiple linear regression, building a model We're calculating a predicted value, calculating errors, and assessing our model. You'll look through that because at the end of that video, you'll have an assignment, something you'll have to complete. And it's basically modifying the script I've given you to do some new things with it. Before we go on to the next video, Brandon Fultz uses a couple of terms. I want to make sure everybody understands what we're talking about. The first one is p-value. And I talk about p-value actually in the fourth video as well. P-value is basically the level of confidence we have in the results we got from a statistical test. And so loosely interpreted, p-value is the chance that the results we got aren't meaningful. And they can translate anywhere from like 0.05 equating to 5%, all the way up to p-values can be as high as 1, which basically means there's a 100% chance that the results we got were not meaningful. Typically, you see p-values around, anywhere from like 0.3, which would be 30% chance that your results are no good, all the way down to amounts that are so small that you know that there's a very, very small chance that your results are not meaningful, and so you can trust your results. And in fact, in the example that we see in the fourth video, when we look at p-values, they are very small, so we know that we have good results. Error is, we've already talked about error. It's the difference between your predicted value and your actual value. But the reason why I bring it up again is because I want to show it to you in the way that we see it the most common. And the way we see it the most common is our linear regression model for a single variable will be written in the way that I've written it down there. Oftentimes y will have a little kind of hat over the top of it, which is to indicate that it's a predicted value. But y predicted value is equal to the intercept plus the input variable times the slope plus the error. And that's how we get the most accurate values for that for our model. Okay, so now you should go through I should get you through the Brandon Fultz videos and give you everything you need to know to do those. Once you do those, come back to the Canvas module and watch the video that I have posted, because that's what's got your assignment in it. Also, the resources that you're going to need for this particular module, those are posted to the Canvas module as well. Okay?